Hey everyone, this is Mrs. Newitt.
Hey, Mr. Newitt's here too.
And today we're going to take a look at examples that use tension. Our problem is a 21 kilogram stoplight hangs from cables. The angles are equal angles of 35 degrees. It says calculate the horizontal tension, vertical tension, and overall tension in each cable. And most cases here you're going to want to have a free body diagram to start with. So we would start by diagramming one side, and we'd put in our horizontal to the right and our vertical up. Notice that the cable itself forms the resultant. We'll add the arrow here to show the resultant. Because our angles are equal, we really don't need to diagram the other side. And that's also going to give us a hint as to how we start. Because if we take a look at the full free body diagram, the stoplight has a certain weight in the downwards direction. And we can find that by taking 21 kilograms times 9.8. And we find that that amount would be 205.8. So if we have equal angles, then that means that our vertical tensions upwards must add together to give us that. So if we look at this side of our diagram, here's our vertical tension, here's our horizontal tension. Each one of these vertical tension amounts, so the one over here and the one over here on the other side, they must each equally share in supporting the weight of 205.8 newtons. And so really all we have to do to find the weight or to find the vertical tension is take the weight divided by 2, and we end up with 102.9 newtons for the vertical tension.
Okay, next we're going to try to figure out what the horizontal tension would be. So knowing that our vertical tension, I'm going to redraw this triangle here that we have. We know our angle is 35 degrees. We now know the vertical component of tension to be 102.9. We now want to find the horizontal tension. So a little trigonometry here using our 35 degrees and knowing that the opposite side is 102.9, we can set up this equation that the tangent of 35 degrees would be equal to 102.9 newtons divided by the tension in the horizontal direction. Solving that, we get the tension in the horizontal direction to be 147 newtons. Sorry, that was a bad 7. Next, we need to find the overall tension. This is going to be our resultant side of the triangle. A couple ways we could do this. We could use Pythagorean theorem at this point, now that we know both the horizontal and the vertical. Remember, we found that this was 147 newtons. But probably for a more accurate answer, we should go ahead and stick to the trigonometry here. And so in this case, we're going to end up using the sine of 35 degrees is equal to the opposite side, 102.9 newtons, divided by our resultant or our hypotenuse, which would be the overall tension in the wire. Solving for this, for that component, we get 179.4 newtons. So in the end, we have 102.9 newtons for our vertical component, 147 for our horizontal, and our total tension is 179.4. Remembering that that is going to be the exact same measurements on both sides of the stoplight here because we do have equal angles. All right, right, Mr. Newman here.
And this is Newman.
And we got some more fun here with some tension. This time, though, we have a 2.5 kilogram sign hanging from some cables, but the angles of the cables are not the same. One's at 30, one's at 55 degrees. We have to calculate this overall tension. Okay, first thing again, we want to draw a free body diagram of what we have going on here. So we know that there is going to be components to these cable tensions. We're going to have a tension, we'll call it T1 in the X direction. We'll call this T1 in the Y direction, and then an overall tension there for cable 1. We'll also have the same thing for cable 2. We'll have a tension 2 in the X direction, a tension 2 in the Y direction, and then an overall tension 2. Our sign, we know, weighs 2.5 kilograms, so it has a normal weight again that can be calculated by taking the 2.5 kilograms times 9.8, and that is going to be 24.5 newtons hanging down. Next, we know then in the Y direction that T1Y plus T2Y has to equal that 24.5 newtons. And how do we calculate T1Y? Well, T1Y will be T1 times the sine of 30 degrees plus T2 times the sine of 55 degrees. And we know that that will have to equal 24.5 newtons. So we now have an equation that shows the two vertical tensions, T1Y and T2Y, must equal the weight of the sign. So our vertical up equals our vertical down. Now, horizontally, we also know the same thing must be true, is that T1 in the X direction must equal T2 in the X direction. Okay? T1 in the X direction can be written as the tension of the first cable times the cosine of 30. And T2 could be written as the tension in cable 2 times the cosine of 55 degrees. And the reason we know that is because the sign is in equilibrium. It is not moving left to right, so we know that those horizontal tensions have to balance each other out.
Okay, so now we hit the real fun part of this, which is the algebra. Notice that we have two equations, one right here written from the vertical information, one right here written from the horizontal equation. The benefit of writing these in the form with the sine and the cosine is that now we have two equations and we really have only two unknowns. So even though these are representing four different components, we just have T1 here and here and T2 here and here. So now you can use pretty much any algebraic method you want to solve this system of equations. In this case, probably substitution is going to be the easiest. And the easiest one to start with here will be our second equation. So we'll write out here T1 equals, we'll divide both sides by the cosine of 30. And so if we divide both of these by the cosine of 30, we end up with T1 equals T2 times the cosine of 55 divided by the cosine of 30. Now we can go ahead and we can substitute into our second equation. We have T2 times cosine of 55 divided by cosine of 30. That is all representing T1 up here, and then we can write out the rest of our equation. Times sine 30 plus T2 times sine 55 is equal to 24.5. Okay, so now we're ready to get our numerical answer. Notice that here, connected to T2, we have three trig functions. So if you type all three of those into your calculator and are very, very careful about the order, you will get T2 times 0.3311. And added to that, we have the sine of 55, which is 0.8192. Those two added together will be 24.5 newtons. So combining our two T2 terms, here we have T2 times 0.3311, here we have T2 times 0.8192, we get 1.15 T2 is equal to 24.5 newtons. Now we can solving that, we get T2 equals 21.3 newtons. Notice that that is automatically the resultant. We haven't yet found any components, so these horizontal and vertical components we really weren't asked to solve for. If you needed to, you could use that 55-degree angle and calculate those out. Also notice that once we have the value for T2, we can go back to either of these equations here and substitute in T2 and solve for T1. And if we work out that algebra, we find that T1 is 14.1 newtons. Again, we don't have the horizontal or vertical components. That's not really part of the answer for this one, but if you were worried about the algebra, you could certainly find those components to double check. The two vertical components, so this here and this here, should add to be 24.5. And the two horizontal components, so these two here, should be equal to each other. Hey everyone, here's your Sioux Falls physics teachers, and today we're looking at an example of an Atwood machine. We have here a pretty simple Atwood machine, just two masses hanging directly downwards from one of those famous frictionless pulleys, and we need to calculate the acceleration and the tension in the cable when they are released. Now the first thing we need to do is draw a pair of free body diagrams. We'll begin with the larger mass over here. Notice that the first piece of information that we would want would be to add the weight. And in this particular case, we do need to label which one we want to be object 1 and object 2. So we'll start with the smaller 0.3 kilograms as mass 1. The larger 0.4 kilograms can be mass 2. Taking 0.4, multiplying times 9.8, we find then that the weight for our heavier object, object 2, is 3.92 newtons. Now notice that of course this is certainly connected to a cable pulling it upwards, but that this object, the heavier one, would be falling. So we're going to add tension to our diagram, but a couple of things. First of all, we don't know the actual amount, and second of all, we want to make sure that we have drawn that tension arrow so that it is shorter than the weight. When I look at that free body diagram, I want to be able to easily see that this object has an acceleration in the downwards direction. It has a larger amount of weight, then it has tension, and so it is falling downwards, and not only is it falling, it is also speeding up as it falls. Now we're ready to draw our second free body diagram, and this is for object 1. Notice that 0.3 kilograms is the smaller mass. If I multiply that times 9.8, we find that its weight is 2.94 newtons. And now we have something similar going on in the upwards direction. It certainly will be traveling in the upwards direction. Notice it's the one that's the lighter of the two masses. So as this heavy mass here falls down, the lighter mass here will fall up. And so this one is going to be traveling in the upwards direction and accelerating, which means that when I add the tension to this diagram, the tension arrow needs to be larger than the weight. Again, we don't know what that tension value is, but we do know it must be a greater amount in order for it to be accelerating upwards.
Okay, so then now we have a situation here where we need to create a system of equations, because essentially we have two unknowns here, the tension of the rope and the acceleration that these masses are undergoing. And so we need to solve for both variables. Well, it happens that we can create two equations with those variables. One equation per mass that is there. So let's start with the 3 kilogram mass here. And we know that in that situation that the tension in the rope minus the weight is going to give us that net force that is acting on that 0.3 kilogram mass. And so that net force has to equal the mass, 0.3 kilograms, times its acceleration. For the 0.4 kilogram mass, we have a similar situation, but because it is moving in the opposite direction, in other words, the weight of the 0.4 kilogram mass is going to be more than the tension, then we take the 3.92 newtons, the weight, minus the tension in this case, and that'll equal the mass of 0.4 times the acceleration. And so now we have a situation where we have two equations with two unknowns that we can then solve. Okay, so to solve these, there's several different ways you could do this, but we'll just show you or model you here substitution. So let's take our first equation here and solve that for t. So t is going to equal 0.3 times a plus 2.94 newtons. And then I'm going to substitute this value for t into my second equation. So I'll end up with 3.92 newtons minus 0.3a minus 2.94 newtons, and that is going to equal 0.4 times a. And so now I have a single equation that has only one variable, that being a in it. And so I can combine these numbers together and solve for a, and I get an acceleration of 1.4 meters per second squared. Okay, now that I have my acceleration, I can simply plug that into either of my first two equations up here and solve for the tension. And when we do that, we'll get a tension value in the string of 3.36 newtons. So we have solved for acceleration, 1.4 meters per second squared, and tension in the string, 3.36 newtons. Alright, Sioux Falls physics teachers are here again. There's another problem for you with an Atwood machine. This time though we have a box that is resting on a table that is connected to a frictionless pulley, and there's a 1 kilogram mass hung from the pulley. The box itself has a mass of 0.5 kilograms. The other factor that we're going to throw into this problem is that the box is also experiencing a frictional force, since it's sitting on the table as it moves, of 2 newtons. We are asked to determine two things: the acceleration of the box and the tension that will exist in the cable when these objects are released. So, first place, again, we always want to start with is free body diagrams of our objects. So we have two objects. We have the box that's on the table. We have the 1 kilogram mass that's hanging from the string. Let's start with the box that's resting on the table. Of course, the box is going to have a certain amount of weight that is down, and if the box itself is 0.5 kilograms, that means that weight would be approximately 5 newtons. It's also going to have a normal force from the table directed upward that would also be 5 newtons. So those forces essentially cancel each other out. There's also going to be a tension from the string that is connected to the box. We don't know what the value of that is. That's one of the things the problem's asking us to find. And we also know that there is a frictional force that is going to oppose the motion of the box. That frictional force is given to us at a value of 2 newtons. Now, let's take a look at the 1 kilogram mass that is hanging from the string. It has essentially 2 forces acting on it. One being the weight of the mass down. If it's 1 kilogram, that's approximately a weight of 10 newtons. And it is also going to be experiencing the same tension in the string that the box has. And that is an unknown quantity to us, but it will have a tension directed upward.
So now we're ready to set up our system of equations again, and we'll start with the crate that is sitting here. Remember that it is traveling to the right, also with an acceleration. So as we write out our equation, looking at the 2 forces that would be involved, the important ones are the tension, which is unknown, and the friction. We do have normal force and weight, but they're in the upwards direction, which has nothing to do with the movement of the object in this case, so we can sort of ignore those 2. Also remember that even though we don't know the amount of the tension, we do know that in order for the acceleration to be to the right, we need to have more tension than friction. So the first part of our equation then is simply looking at our free body diagram and stating that the net force is tension minus the force of friction, which is 2 newtons. Now notice that gives us one way to write the net force. The other way to write the net force is by writing mass times acceleration. Mass in this case is 0.5 kilograms times acceleration, which is unknown. Our second object will also have an equation written for it. Again, before we write that down, our equation is basically writing the net force. In this case, if the object is falling, it should have a downwards acceleration, which means that that weight needs to be greater than tension. So to write this equation, first we'll look at our forces. Weight, which is 10 newtons, minus tension is our net force. Net force also is equal to mass times acceleration. Mass in this case is 1 kilogram multiplied times acceleration, and that gives us our second equation. And again, at this point, you can choose whatever method of solving the system that you want, but we do have 2 unknowns and 2 equations. One possibility would be through substitution. We could pick either of these equations and rearrange it for t. If I choose the top one here, we would get t equals 0.5 times acceleration plus 2 newtons. Then we can take our second equation and substitute in for t, so 10 minus 0.5a plus 2. Notice that that tension part needs to be in parentheses because the whole thing is going to be subtracted. That is equal to 1a. Solving that for acceleration, we get 5.3 meters per second squared. Also notice then at this point, we could choose either one of our equations to go back and solve for t. In this case, probably just as easy to take this value for acceleration and plug it in here for a. Then our equation would be 10 minus t, there's our unknown, equals 1 times 5.3 meters per second squared. Solving that for t, we get a value of 4.67 newtons as the tension in the string. Well, hello everyone. Here's your Sioux Falls physics teachers looking at another example of an Atwood machine, this one on an incline. So we are going to have quite a few steps, but it follows the basic principles of our other Atwood machine situations where we need to write an equation for each object, summarizing the net force on the object, and then solve for our acceleration and tension. Now, the first thing we want to do is actually draw our free body diagram. And we're going to begin with the easiest example, and that is the object that is hanging directly down. Now, notice one thing that's a little bit simple about this problem is that both masses are 1 kilogram. So in this particular case, if we draw a free body diagram for that, multiplying times gravity, the weight of this object, and we'll make this object 2, is going to be 9.8 newtons. Now again, we have tension going upwards. That's provided by the cable. But this particular object is falling in the downwards direction. So its acceleration would be down also. And that gives us a hint about tension. If the overall object needs to be falling and accelerating in the downwards direction, then we need to make sure that the weight is larger than that unknown tension amount. Now we should note something here, because on things with an incline, sometimes it's a little bit difficult to tell exactly which way they're going to go. If for some reason the incline was such that the objects actually went the reverse direction. So in other words, if it was steep enough, we might find some situations where this object travels up and this object slides down the ramp. If that is the case, at the end, if we have done our free body diagram incorrectly, we will simply get an acceleration value that's negative. So don't feel like you need to know for sure what direction the acceleration is when you start a problem. If you guess correctly, great, you'll get a positive value for A at the end. But if you happen to guess wrong, you'll get a negative value for A, and then you'll just know that the situation is actually reversed from the way that you had your diagram set up. So let's go ahead and look at that free body diagram. And again, remember, anytime we have an incline, we need to go back to our triangle free body diagram so that we can see the correct components. We do see that the weight would still be the same, 9.8 newtons. And again, that is directly downwards. Now for the two components, one component is going to act down the ramp. That's the one that we're going to be interested in. And one component will be perpendicular. Notice that in this particular case, that component is not really important to us. We also know that the angle of the ramp over here is 30 degrees, and that angle always corresponds to the bottom angle in our triangle. So that is 30 degrees also. So if we are interested in this vector here, this is the component of weight that can act to pull that object down the ramp. That component would be found using the sine of 30 degrees. So just a little bit of extra trig down here. We would have the sine of 30 degrees, because we're dealing with the opposite side. That is equal to opposite. And again, sometimes we would call that the x component, even though it's not just completely in the horizontal direction. It is a component of gravity, divided by the hypotenuse, and the hypotenuse is over here. That's the 9.8 newtons. And so solving then for that component, we find that that component is equal to 4.9 newtons. So the amount of weight that can actually act to pull this object down the ramp, that amount is 4.9 newtons. Now it does also have tension pulling back up over the pulley from the rope, And notice that if we're assuming that this object over here was going down, then we need to assume that this object over here is accelerating up. And if that is the case, then the tension must be greater than the 4.9 component of weight. So notice that's slightly different than just the normal Atwood machine problems that we've been doing so far. We do not compare tension to this 9.8 newtons here, because that 9.8 newtons is directed straight down. Instead, we compare tension to the 4.9 because it is that component that is directly opposite the tension. With that in mind, we're now ready to write our equations. We'll start with object number 2, that's over here. And again, if we're going to assume that it's going downwards, then its weight needs to be greater than its tension. And so to describe the net force, we would say 9.8 newtons minus tension. That would give us the net force. So that's going to give us the extra that's causing it to accelerate. That is equal to mass times acceleration. And in this case, the mass is simply 1. And so that's our first equation. For our second equation, the tension, again, pulling up the ramp, is larger. So we would say tension minus, now be careful, don't put in the full weight, but again, just put the component of weight that is acting opposite, which is 4.9 newtons. That is equal to the mass times the acceleration, and again, its mass is equal to 1. Now we're ready to go into the algebra. This time I'll probably choose to solve this equation for t. T is equal to 1a plus 4.9. Then we can take our other equation here and substitute in for that. Again, remembering that when we subtract t, we need to subtract everything. So this whole thing here all goes in parentheses. That is equal to 1a. And now we can do a little bit of algebra. Notice that this subtraction sign over here then needs to be distributed to the 1a and the 4.9. So we got 9.8 minus 1a minus 4.9 is equal to 1a. Solving that, we get an acceleration of 2.45 meters per second squared. And now we can go back to either of these equations for tension. We'll probably take the second one here this time. So tension minus 4.9 is equal to 1 kilogram times our acceleration of 2.45. Solving that for t, we end up with 7.35 newtons of tension. Do notice that our acceleration turned out to be positive, so that means we guessed correctly, and that this object over here is indeed falling down. This object over here is indeed being pulled up the ramp in this particular case.